Hey guys, welcome back to my channel, and today I'm going to be teaching the differentiability of multivariable functions. So first I'm going to show the definition of differentiability in multivariable calculus, and then I'm going to explain where that formula comes from. Then I'm going to explain why we can't just apply the definition of differentiability of single variable functions to multivariable functions, and I'm also going to use an example to show why we can't do that. Lastly, I'm going to go over an example of proving the differentiability of a multivariable function. So the definition of differentiability for multivariable functions is a function f given by z equals f of x comma y will be differentiable at a point if delta z can be written in this form. So also keep in mind delta z is essentially the change in z as you go from one point such as f of x comma y to another point, such as f of x plus delta x, comma y plus delta y. So again, that change in z will be able to be written in this form, the partial derivative at that point with respect to x times delta x, plus the partial derivative at that point with respect to y times delta y, plus epsilon 1 delta x, plus epsilon 2 delta y, and both epsilon 1 and epsilon 2 will have to approach 0 as delta x comma delta y approach 0 comma 0. So we're going to see what this epsilon 1 and epsilon 2 are in this video, but they basically represent error, which is why we want these errors to approach 0. So we're actually going to go back to single variable calculus to see what differentiability meant back then. So for a single variable function, a function was differentiable at a point if you could take the derivative at the point. So we're going to go over the definition of the derivative, specifically the limit definition. So remember the limit definition was just the limit of the difference quotient as h approaches 0. So the limit of f of x plus h minus f of x over h, as you take h to approach 0, that had to exist for the derivative to exist at that point. So we're also going to take a look at what the derivative was graphically. So let's pretend our function is x squared. And let's just have x be over here, and then x plus h be over here. So this was f of x, and this was f of x plus h. So f of x plus h minus f of x over h is actually the slope of the secant line. So it looks something like this. And then as we decrease this, as we decrease it and have it approach 0, that secant line actually approaches the tangent line. So the tangent line just represents like the instantaneous rate of change rather than the average rate of change. So that is basically what the derivative represented in single variable calculus. So the derivative was just the slope of the tangent line at that point. Okay, so now we're going to rearrange this definition of the derivative into something that looks similar to this definition of differentiability of multivariable functions. So what we're going to do is we're actually going to write the numerator, that is f of x plus h minus f of x, on the left side. And then on the right side, we're going to be cross-multiplying this equation, so we get f prime of x times h. And then we actually have this epsilon 1, which, as I said previously, represents an error term, and it's basically a function of h. So in this definition above, essentially the error term is like a function of delta x and delta y. So this f of x plus h minus f of x equals f prime of x times h. This part looks very familiar because it looks like linear approximation back in single variable calculus. And that's exactly why we have the error term, because if we only included that part, that would just be an approximation. So graphically, this error term also just represents the difference between the approximation with the secant line versus the actual derivative, which is given by the slope of the tangent line. Now we're going to apply this formula we derived from the derivative definition in one variable to multivariables. So we're first going to write it for the partial derivative with respect to x. So the partial derivative with respect to x, remember, instead of h, we're changing delta x and having delta x approach 0. So this is just the definition, minus f x comma y over delta x. So we're going to do the same thing and rearrange it so that we get something similar to above. So we're going to write f of x plus delta x, comma y, minus f x, comma y, will equal the partial derivative with respect to x times delta x, and then plus our error term. And then now it's in terms of delta x rather than h. And as you can see, this is very similar to what we have here. So we essentially got this over here as well as this. So now we're going to write the exact same thing for the partial derivative with respect to y. And we're essentially also just going to be getting the parts of this formula which have the y components. So we're going to do the partial derivative with respect to y equals the limit of f of x0, y0 plus delta y minus f of x0, comma y0 over delta y. And then we want delta y to approach 0. And then when we cross multiply, we get the same thing as above. And then this time, our error term, we're just going to do epsilon subscript 2, and then it's going to be a function of delta y, because this time we're taking the partial derivative with respect to y. So there's going to be an error with respect to y. Okay, so now we're going to combine these two expressions or equations to get the total differentiability definition. So when we do f of x0 plus delta x, and then y0 plus delta y, minus f of x0, y0, we're basically just defining this delta z. So that's basically what delta z is. And then because we're adding the left sides of the two equations we found above together, we can also add the right sides of the equations together. So we get delta z equals f sub x, x0, comma y0, delta x, and then plus f sub y, x0, y0, delta y, plus epsilon 1, delta x, plus epsilon 2, delta y. And this is essentially where we just got this differentiability definition from. So essentially what this formula means is that delta z, or the change in z as we go from a point such as f of x0, comma y0 to f of x0 plus delta x, y0 plus delta y, actually consists of the approximations given by the partial derivative with respect to x times delta x and the partial derivative with respect to y times delta y. And then because those two are only approximations, we have these two error terms at the end, which are epsilon 1 as a function of delta x and epsilon 2 as a function of delta y. So these two error terms do give us the last part of the definition. So both error terms need to approach 0 as delta x and delta y approach 0. So the reason we want these error terms to approach 0 goes back to where we got this formula from, and it's because it's very similar to how we approximate the change in z by using the partial derivatives with respect to both x and y. And if the error is too big, we're basically saying that the actual change is way too far off from the approximated change, which is why we need the error to be close to 0 or to approach 0. So now we're going to think of this critical thinking question, which is what would happen if we said that the definition of differentiability for a single variable function could be applied to a multivariable function. So that is, remember, for single variables, if the derivative existed at that point, then the function was differentiable at that point. So what if we said for multivariable functions, if the partial derivatives with both respect to x and y, if they both exist, would that mean that that multivariable function is also differentiable there? So for this one, we're going to actually take a look at an example. And before we take a look at the example, I'm going to explain something else. But first, we're going to see the example. So this is a function negative 3xy over x squared plus y squared. And then this is when x comma y are not 0. And then when they are, the function just equals 0. To show that just having the partial derivatives existing at a point does not imply differentiability, we're going to need to know that differentiability implies continuity. And basically what this means is that if a multivariable function of x and y is differentiable at a point x0, y0, it will also be continuous at that point. So we're going to prove this theorem, and this theorem comes from the definition of differentiability as shown above. So we're going to have a function that's differentiable at x0, y0 called z, and we're basically going to write delta z the same way as the definition of differentiability, except we're going to group these terms so that we can factor out a delta x and a delta y. And then also, as usual, we know that epsilon 1 and epsilon 2 will approach 0 as delta x and delta y approach 0 because we said that z is differentiable at x0, y0. However, we know that delta z is also just f of x plus delta x, comma y plus delta y minus f of x, comma y. Now we're going to define delta x to be x minus x0 and delta y to be y minus y0. If we rearrange terms, we see that x is x0 plus delta x and y is y0 plus delta y. So now with these substitutions, we can write delta z as f of x comma y minus f of x0 comma y0, and then our right side will also be changed because delta x will be x minus x0 and delta y will be y minus y0. So now we're just going to add the term f of x0 comma y0 to the right side. So now we're going to take the limit of f of x comma y as x comma y approaches x0 comma y0. If x approaches x0, then obviously this entire term will cancel to 0. And then this other term will also cancel to 0. And what we have left is this term here. And this term will not cancel to anything because it doesn't even have a normal x or y. So we just get this. And this result we get is actually the definition of continuity because as the limit approaches this point, it actually equals what that function is defined to be at that point. So this theorem also essentially works the other way because if every differentiable function at a point is also continuous at that point, it means that if a function is not continuous at a point, it can't be differentiable at that point. We're going to use this idea to show that just because the partial derivatives exist at a point does not mean it's differentiable at that point. And again, we're going to be using this example here. To prove that this function is not continuous at 0, 0, we're going to first try to take the limit of this function as x, y approaches 0, 0. So we're going to first approach along y equals x, and we're going to see what happens. So the limit of x, x, because y is now x, approaches 0, 0, of this function will just be limit x, x approaches 0, 0. Because y is x, we get negative 3x squared over x squared plus x squared. So this x squared plus x squared is just 2x squared. And then you can see that these x squareds cancel out. So the limit would just be negative 3 halves. So now we're going to try to go along another path, so y equals negative x, and see if we get the same thing. Along this path, we would get negative 3x, but then y is negative x. This would be positive 3x squared, and then over x squared plus negative x squared. So the top cancels to 3x squared, while the bottom cancels to 2x squared. So we get 3x squared over 2x squared, and the x squareds cancel out, so we get 3 halves. So remember, if the limit is different along different paths, then overall the limit does not exist. So we already proved that it's not continuous because the limit doesn't exist at a point. There's no way it'll also be continuous at the point. So thus, we know that this function is actually not differentiable at the point. However, the partial derivatives do exist because we're going to prove that they do exist. So the partial derivative with respect to x at 0, 0, we're going to use the limit definition. So delta x approaches 0, f of delta x, 0 minus f of 0, 0 over delta x. So f of 0, 0 is just 0, so we get a 0. And then if we have y equaling to 0, the numerator becomes 0 entirely, and the denominator becomes delta x squared. So that means our entire thing just becomes 0, and 0 over delta x is just 0. So as you can see, the partial derivative with respect to x exists. Now we're going to see with respect to y. again, we're going to use the limit definition. And again, if delta y is 0, so this one obviously cancels to 0. And when x is 0, then our entire numerator becomes 0, while our denominator becomes delta y squared. And thus the whole thing is just 0. So from this example, we proved that even though the partial derivatives existed with both respect to x and y, the function was not differentiable at that point. So this is how we proved that using the single variable calculus definition of differentiability would not work for multivariable calculus. So now that I've basically explained where this definition of differentiability for multivariable functions comes from, we're going to try doing an example. So the example we're going to do is f of x comma y equals x squared plus y squared. And we want to show that it's differentiable. We want to first define our delta z, or our change. And again, that's just going from one point to the other. So it's just x plus delta x, and then y plus delta y, minus f of x comma y. And we're just going to plug in x plus delta x wherever x is, and y plus delta y where y is, and then subtract the normal function. We're going to distribute this, and then minus x squared minus y squared. So our x squareds cancel out and our y squareds cancel out, and we're left with 2x delta x plus delta x squared plus 2y delta y plus delta y squared. So what we're going to do is we're going to try to put it in the form of our definition. And essentially, it's just in this form. So we want the partial derivative with respect to x times delta x, and then the partial derivative with respect to y times delta y. And then we want to put our error and then delta x, and then our error function, and then delta y. In this case, we're going to realize that the partial derivative with respect to x is 2x. And we see that right over here. So this is our f sub x times delta x. And then we also see that the partial derivative with respect to y is going to be 2y. So we can write this next term as f sub y, and then it'll just be times delta y. So this delta x squared can be written in terms of delta x times delta x, where this one over here is our epsilon 1, and then this delta y squared can be delta y times delta y, where this is epsilon 2. So we basically already wrote it in the definition of differentiability now, and we need to show that our epsilon 1 and epsilon 2 do indeed go to 0 as delta x and delta y approach 0. So epsilon 1 equals delta x, and epsilon 2 equals delta y. So if we have delta x and delta y approach 0, then epsilon and epsilon 2, obviously you can tell they will also approach 0. So thus, because our epsilon 1 and epsilon 2 approach 0 as delta x and delta y approach 0, we can conclude that our function is differentiable. So I hope you enjoyed my video on the definition of differentiability of multivariable calculus. And yeah, thanks for watching.